Intermolecular forces, types and relative strengths. In this lecture, we will discuss the four types of intermolecular forces. First, we will need to understand the physical nature of these intermolecular forces and how they arise from a concentration of electron density in a molecule. Then we will discuss the properties and relative strengths of the four types of forces. We will focus on four main classes of intermolecular forces. All of these arise due to the concept of a dipole moment. A separated pair of opposite electrical charges form an electric dipole, which generates an electromagnetic field. This electromagnetic field behaves like a magnet, with the positive end of one dipole attracting the negative end of another. The dipole moment is effectively a measure of how strong this magnet happens to be. Because molecules are composed of positively charged nuclei and negatively charged electrons, they have the ability to form small dipoles. First, let's consider the water molecule, which has a bent geometry due to the two unshared pairs of electrons. The lone pairs and the large electronegativity of oxygen cause the oxygen atom to have a much larger electron density than the two hydrogens. This results in a region of greater negative charge, which we denote with the lowercase Greek letter delta with a superscript negative sign, and a region of greater positive charge, denoted as delta plus. Consequently, water forms a dipole and acts like a tiny magnet. We will consider two types of molecular dipoles. First are the permanent dipoles. As in water, these dipoles do not change with time. They are formed due to large differences in electronegativity and electron density in a molecule. The more symmetric a molecule is, the less likely it will have a permanent dipole. The second type are induced dipoles. All atoms and molecules experience induced dipoles. These are not permanent, meaning that they will fluctuate in time and will depend on the proximity of the two molecules. Induced dipoles tend to be short-lived and weaker than permanent dipoles. The table below lists the four types of intermolecular forces that we will discuss in order of increasing strength. Please be aware that the relative strength of the forces assumes that the molecules being compared are roughly the same size. First, we have dispersion forces. These are the weakest forces, but they occur between all atom or molecule pairs. Next in strength are dipole-dipole forces. These only occur between molecules with a permanent dipole. Next comes hydrogen bonding. These are the strongest forces present between neutral molecules and are a special class of dipole-dipole forces. And the strongest type are ion dipole forces. And these are an interaction between a permanent dipole in one molecule and an ion present near it. We will begin by discussing dispersion forces, which are also called London forces or induced dipole forces. As stated before, these occur between all atom or molecule pairs. Dispersion forces tend to be the weakest of the intermolecular forces and arise due to induced dipoles. The creation and magnitude of induced dipoles in atoms and molecules are due to the polarizability of the electron cloud around the atom or molecule. Recall that the weaker the effective nuclear charge in an atom, the more freely the valence electrons can move. Atoms with a low effective nuclear charge will have a valence shell in which the electrons can slosh around very easily. The polarizability of an atom is effectively a measure of the sloshiness of the electron cloud. The more electrons in an atom, the larger the valence shell, and therefore the higher the polarizability. Let's consider two helium atoms. Recall that helium has 2 electrons in its valence shell. The electron density around the helium atoms is generally equal, causing no imbalance of charge. This is visualized on the right, where the electrons tend to be on opposite sides of the nucleus. From time to time, the electrons will both exist on the same side of the atom, as shown in helium A. This generates what's known as an instantaneous dipole in the helium atom. This instantaneous dipole then induces a dipole on the neighboring helium, resulting in a brief attractive force. This gives rise to the dispersion forces between the two atoms. The dispersion forces tend to be weak because the instantaneous and induced dipoles are not very strong themselves, and due to the fact that they last a very short time and tend to flicker on and off very rapidly. Because all atoms are polarizable, all atoms and molecules will experience dispersion forces. As we will see in a few minutes, even though individual dispersion interactions are quite weak, the collected effect of multiple dispersion interactions can cause relatively strong attractions. We will now investigate the magnitudes of dispersion forces and how they are determined by two main factors. In order to demonstrate this, we will consider the boiling point of several compounds. However, before we do so, we need to understand the relationship between intermolecular forces and boiling point. Boiling is the change from the liquid phase to the gas phase. This requires adding enough kinetic energy to permit the molecules to leave the potential well and not get stuck back in it. Molecules with stronger intermolecular forces will require a greater amount of heat energy to be added to overcome the stronger forces and boil the liquid. Consequently, molecules with stronger intermolecular forces will tend to have a higher boiling point. The first factor that will determine the magnitude of dispersion forces is the molar mass. The larger the molar mass of a molecular atom, the greater the dispersion forces tend to be. This can be understood through the polarizability. A larger molar mass generally means a smaller effective nuclear charge, therefore a greater polarizability. To demonstrate this, we will consider the boiling points of the halogens and the noble gases, since these are atoms and molecules that only experience dispersion interactions. The table on the left lists the noble gases in order from helium to radon. The second column gives the molar masses, which increase from 4 grams per mole for helium up to 222 grams per mole for radon. The third column lists the boiling point for each of the gases. Note that these increase from 4.2 Kelvin for helium up to a value of 211 Kelvin for radon. The boiling point increases as the molar mass increases due to the increase in dispersion forces. The table on the right lists 4 of the halogens: fluorine, chlorine, bromine, and iodine, along with their molar masses and boiling points. Again, the molar masses increase from 38 grams per mole for fluorine to 253.8 grams per mole for iodine. And likewise, the boiling points increase from 85 Kelvin for fluorine to 458 degrees Kelvin for iodine. The effect is much more noticeable in the halogens. We see this due to the fact that both fluorine and chlorine are gases at room temperature, where bromine, which is much larger and has stronger dispersion forces, is actually a liquid at room temperature. Iodine, which is the largest and experiences the strongest dispersion forces, is actually a solid at room temperature. The second factor that determines the magnitude of dispersion forces is the surface area. The larger the surface area of a molecular atom, the greater the dispersion forces tend to be. The greater the surface area for a molecule, the more places it has to induce dipoles in other molecules, and therefore the stronger the attractive forces will be. This is primarily observed through the shape of the molecule. In three-dimensional space, a sphere will have the smallest possible surface area for a given volume. This means that, all other things being equal, a molecule that is more ball-like in shape will have smaller dispersion forces than a molecule that is more rod-like in shape. To demonstrate this, we will consider 4 isomers of hexane, which has a molecular formula of C6H14. Because they all have the same molar mass, it will be the shape of the molecule that will determine the relative strengths of the dispersion forces, and therefore the boiling points. We begin on the left with N-hexane, which is just a sequence of carbons and hydrogens in a straight chain. Because this is a very rod-like molecule, it will experience the greatest amount of dispersion forces. Its boiling point is 342 Kelvin. The second in our list is 2-methylpentane, in which one CH3 group has been moved to a different location. We now have a molecule that is a little less rod-like, and in this case has less opportunity to generate dispersion forces, and the boiling point has decreased to 332 Kelvin. Next, we move an additional CH3 group to form 2,3-dimethylbutane. This is now a much more ball-like molecule, and we see that the boiling point has decreased to 331 Kelvin. Lastly, we form 2,2-dimethylbutane, which is now quite spherical, and we see that the dispersion forces are much less, and the boiling point has decreased to 323 Kelvin. One of the goals of this discussion will be to determine the strongest possible intermolecular forces in a molecule. But we must always be careful when estimating the strength of dispersion forces. As we stated before, individual dispersion interactions are quite weak, but if a molecule is large enough, its dispersion forces can become quite large collectively. In a few minutes, we will see that ammonia, NH3, experiences hydrogen bonding, which is a considerably stronger force than dispersion. Ammonia has a boiling point of 240 Kelvin. As we just saw, the molecule N-hexane, C6H14, only experiences dispersion forces, yet its boiling point was 342 Kelvin. So why is this? Well, it turns out that N-hexane, C6H14, is a much larger molecule than ammonia, NH3. The increased size allows for many more dispersion interactions, the sum of which becomes stronger than the hydrogen bonding in ammonia. Next, we will discuss dipole-dipole forces. And these forces arise only in molecules that possess permanent dipoles. We refer to any molecule with a permanent dipole as a polar molecule. Dipole-dipole interactions are generally simpler to understand than dispersion interactions, but they are not necessarily easy to identify, since we must determine if a molecule has a polar region. Any polar region of a molecule will behave like a tiny magnet, and as such will attract other polar regions from other molecules. Dipole-dipole forces tend to be stronger than dispersion forces because the permanent dipoles are stronger in general than induced dipoles, and they do not fluctuate in time. When comparing two molecules of roughly equal mass and size, the dispersion forces will be roughly equal. From this point, the most prominent intermolecular forces will be determined by dipoles. So let's understand why dipole-dipole forces arise. The molecule to the right is acetone, the main ingredient in nail polish remover. Acetone is a polar molecule, and we'll understand better why it is in a few minutes. Acetone has a negative region on the oxygen and a positive region on the central carbon. These are denoted with our delta plus and delta minus as before. When a second acetone molecule approaches, the positive end of one dipole attracts the negative end of the second dipole. And as with magnets, we generate an attractive force, known as the dipole-dipole force. The task of identifying which molecules possess a permanent dipole, and are therefore polar, will become easier as you become more familiar with molecular structure. You will find that there are several easily identifiable molecular groups that will always be polar. When in doubt, you should utilize two important tools that you learned in Chem 1, electronegativity and the Lewis dot structure. When a very electronegative atom is bonded to a very non-electronegative atom, the resulting bond is polar and forms a dipole. Examples of this include the bond in HCl, where the chlorine is very electronegative and the hydrogen is not. The OH bond, again where the oxygen is very electronegative and the hydrogen is not. And the C double bond O as in acetone. In this case, the oxygen is very electronegative and the carbon is not. The other feature common to polar groups is a large electron density on one part of the group. Usually this arises due to unshared electron pairs, or lone pairs. Recall that we can easily locate lone pairs by drawing a correct Lewis dot structure for the molecule. We will review how to draw Lewis dot structures in lecture, but for now we will consider the polarity or non-polarity of several molecules based on their given Lewis structures. Let's consider three examples of polar molecules. I recommend at this point that you pause this video and make an attempt to draw the Lewis dot structure for each of these three molecules. Once you have done so, restart the video. We will display the Lewis dot structure and demonstrate where the polarity arises. The first molecule, formaldehyde, has the following Lewis structure. Notice that the oxygen has two unshared pairs of electrons. These unshared pairs of electrons generate a large electron density on the oxygen, and consequently we have a dipole moment between the carbon and the oxygen, making this a polar molecule. The second molecule, ethanol, has the following Lewis dot structure. Again, notice that the oxygen has two lone pairs. One issue to address is the fact that even though the CH3-CH bond is itself not completely symmetric, it will not generate a large amount of polarity. The greatest amount of polarity in the case of ethanol is due to the electron density on the oxygen, and generates a dipole moment due to that. The third molecule is dimethyl ether, and has the following Lewis dot structure. Again, the tetrahedral CH3 groups do not generate a tremendous amount of polarity. It is the two lone pairs on the oxygen that generate the dipole moment in this case. Now let's consider three examples of nonpolar molecules. In each of these cases, we will see that the molecule does possess regions of electron density, but due to the symmetry of the molecules, these regions of electron density tend to counterbalance each other, so that there's no net dipole moment. As before, I recommend that you pause this video and make an attempt to draw the Lewis structure for each of these three molecules. The first molecule, sulfur trioxide, has the following Lewis structure. Notice that each of the oxygens do possess two lone pairs, and therefore have a region of high electron density. But due to the molecular geometry, in this case being trigonal planar, those regions of density each generate their own dipole, but they all cancel each other out, leaving no net dipole moment, and therefore this molecule is nonpolar. The second molecule, carbon dioxide, has the following Lewis dot structure. Again, the two oxygens both contain two lone pairs, generating regions of electron density. But because this molecule is linear, the dipole moments in each case cancel out, resulting in no net dipole. Lastly, we have carbon tetrachloride, which has the following Lewis dot structure. Again, because each chlorine possesses 3 lone pairs, there is a tremendous amount of electron density around each of these chlorine atoms. But due to the tetrahedral structure, once again, the individual dipole moments cancel out, resulting in 0 net dipole. So all 3 of these molecules are nonpolar and will therefore not demonstrate dipole-dipole interactions. The next class we will consider is the hydrogen bond, and this is the strongest class of intermolecular forces between neutral molecules. When a hydrogen is covalently bonded to nitrogen, oxygen, or fluorine, which are the 3 most electronegative atoms on the periodic table, the resulting permanent dipole is extremely strong. Therefore, the resulting dipole-dipole interaction between the positive hydrogen on one molecule and the negative oxygen, nitrogen, or fluorine on the second molecule is much stronger than normal dipole interactions. This is known as the hydrogen bond. This is demonstrated in the figure at the bottom of the screen, where we have 2 ammonia molecules interacting through a hydrogen bond. Notice that the dipole interaction is between the hydrogen atom on one ammonia and the lone pair on the nitrogen on the second ammonia. The effect of hydrogen bonding can be very pronounced. To see this, let's consider the molecules H2O, or water, and H2S, or hydrogen sulfide. These are analogous molecules, and both have the same structure, and both are polar. However, water can experience hydrogen bonding, whereas hydrogen sulfide cannot. As a consequence, water is a liquid at room temperature, and hydrogen sulfide is a gas. This is due to the fact that the hydrogen bonding in water results in a more condensed phase than the mere dipole-dipole interactions in hydrogen sulfide, which result in a gas phase rather than a liquid phase. The strength of a hydrogen bond lies in the middle ground between the strength of a dipole-dipole interaction and the strength of an actual covalent bond. It is important to remember that a hydrogen bond is not truly a bond, since electrons are not being transferred or shared. It is still just an electrostatic attraction that is weaker than covalent bonding. Hydrogen bonding is extremely important to life on Earth. In fact, without the phenomenon of hydrogen bonding, there would be no life on Earth. Let's consider several examples of why this is. First, large biological molecules, such as proteins and DNA, are held together and are structurally shaped due to hydrogen bonding. This can be seen in the image to the right, where the green dashed lines indicate hydrogen bonds between an NH group in one region of the protein and a CO group in another region. This gives rise to the alpha helical structure that's observed. Additionally, small molecules activate or deactivate the function of proteins by hydrogen bonding to receptor regions of the protein, or by interfering with the development of larger biological structures. The purple molecule to the right is the antibiotic vancomycin. In this particular image, it is hydrogen bonded to a short peptide, the green molecule. This peptide is the precursor to a bacterial cell wall. By hydrogen bonding to this small peptide, the vancomycin has prevented the bacteria from building its cell wall and therefore unable to propagate itself in the human body. Secondly, hydrogen bonding is a critical factor in the formation of solid water. When ice solidifies, it takes up more space than liquid water because the crystal structure expands due to the hydrogen bonds becoming more permanent. This is seen in the image to the right. The frame on the left-hand side models liquid water, while the frame on the right-hand side models solid water. This means that ice is less dense than liquid water, causing it to float. As a result, bodies of water freeze from the top down rather than the bottom up, and life can survive in water over the winter months. The last type of intermolecular forces that we will consider are ion dipole forces. As the name implies, ion dipole forces occur between an ion and a molecule with a permanent dipole. This is demonstrated to the right, where the water molecules are surrounding the sodium ion, with the negative end of the water attracted to the positively charged sodium ion. We will not focus on ion dipole forces in this chapter. We will return to these forces in Chapter 13. Now that we have discussed the four types of intermolecular forces, we come to the last topic in this video, which is how to identify the strongest intermolecular force given the identity of a pure compound. This question should be approached systematically by eliminating the strongest possible forces first. Here we see a flowchart indicating the steps to determine the strongest force in a pure compound. To begin with, we must have some information regarding the molecular structure. In general, this could be a chemical formula or an actual molecular structure that's given to you. Once we have determined the molecular structure, we have to systematically identify the strongest forces through a series of questions. The first question we always ask is, do we have a hydrogen bonded to a nitrogen, oxygen, or fluorine? If the answer is yes, then our strongest intermolecular force present is hydrogen bonding. If the answer is no, we go to our second question, which is, does the molecule possess a permanent dipole? If the answer is yes, then the strongest intermolecular force present are dipole-dipole interactions. If the answer is no, there is only one possible type of force left, and that is dispersion forces. Recall that dispersion forces are present in all atoms and molecules. So in the absence of hydrogen bonding and dipole-dipole interactions, all molecules will possess dispersion forces. Let's consider a few examples. First, what are the strongest intermolecular forces present in phosphine, pH 3? We begin with the Lewis structure for phosphine, which is demonstrated here. Now we proceed through our list of questions. Question 1 is, does phosphine have a hydrogen bonded to a nitrogen, oxygen, or fluorine? Clearly from the structure, the answer is no. We now move to question 2. Does phosphine have a permanent dipole? Due to the fact that the phosphorus has a lone pair, we see that phosphine does indeed have a permanent dipole. Therefore, the strongest intermolecular force in phosphine is the dipole-dipole interaction. Now let's consider what the strongest intermolecular forces are that are present in propane, CH3, CH2, CH3. First, the Lewis structure for propane is seen to the right. Our first question, does propane have a hydrogen bonded to a nitrogen, oxygen, or fluorine? It is clear from the structure that this is not the case. Secondly, does propane have a permanent dipole? Again, recall that each of these CH3, CH2 groups are tetrahedral in structure, which means that there is no net dipole moment that is present in this chain of hydrocarbons, and therefore the answer is no. This leaves us with only dispersion forces possible for propane. And in our last example, what are the strongest intermolecular forces present in formic acid, HCOOH? As before, we begin with our Lewis structure, which is shown to the right. Our first question, as before, is, does formic acid have a hydrogen bonded to a nitrogen, oxygen, or fluorine? Looking at the right side of our structure, we see that we do indeed have a hydrogen bonded to an oxygen. We're now done. The strongest intermolecular force in formic acid is hydrogen bonding. We will practice drawing Lewis structures and identifying the strongest force in a pure compound in lecture over the next couple of classes.